Hello, everybody. Thank you so much for joining us. We have a really special treat for y'all. We have Chris Lamb, the VP of Software for Compute Platforms at NVIDIA, joining us today for his talk, Python at the Speed of Light, Accelerating Science with CUDA Python. Chris runs a worldwide team building platforms for AI and parallel high-performance computing deployed across the cloud, enterprise data center, edge, and embedded applications. His team is responsible for the CUDA platform and the DGS HGX cluster stack for AI. And we're really excited to hear from Chris to learn more about him. Thank you.
Awesome. Thank you so much, Julie. Well, it's great to be here. This is my first SciPy, which is kind of interesting. To unpack that a little bit. I'm super happy. This is actually the second year of our platinum sponsorship, NVIDIA's platinum sponsorship of SciPy, and we're super excited. We brought 15 sessions to share with you all here, and we've got 20 engineers on site who are working in the sprints, and they're out there at the table if you want to engage with them to work on making scientific Python even better. A little bit about my background. I've been working on accelerated computing in some form for over 20 years at this point. I joined NVIDIA in 2007 to work on a little quiet unknown project called CUDA. There were about 6 of us in the software engineering group working on CUDA at that time. I remember going into the cafeteria my first week on the job and people saying, "What are you going to do?" And I said, "Wow, it's a really cool thing. It's called CUDA. I've never heard of it. What's that?" "Well, we're gonna use the GPUs not for gaming, but to run like scientific and engineering codes, and it goes really fast." And I said, "That's a dumb idea. We're NVIDIA. We do gaming. We blow stuff up. We do graphics. That'll never work." But I'm so glad that NVIDIA was doing gaming and graphics at that time because it really gave us a leg up, and I'll touch on that a little bit later in the talk. I think we're at a similar sort of point now. But scientific computing has really surrounded me from an early age. My family includes a couple of high-energy astrophysicists and cosmologists, a radio astronomer. So even before my professional career, I had a front row seat to computational science and how it advances human understanding and enables progress for humanity. Both from like a day-to-day dinner table research group, how are you gonna get that paper for your postdoc done kind of thing. Also with observing instruments and the inspiration that those can provide. And also large-scale computing platforms. Folks in my family were working at NCSA, Los Alamos, NASA, doing incredible things. So for me, it's a passion. It's a personal passion as well. And so I'm super, super proud that what NVIDIA and CUDA has been able to do for the scientific community over the last 20 years. And I'm even more optimistic about what's going to be coming up. So I'm here to tell you about how NVIDIA is building machines to accelerate science, not just the AI part, and critically how we're evolving the CUDA platform to bring Python in as a first-class language and environment for people to do work, and why that's so important. How Python and the SciPy community are at the forefront of accelerated computing for this scientific computing ecosystem, and how there's an exciting opportunity to take advantage of. And we're at a critical time for that. And the reason is we're at an inflection point. Python, which is the programming language of AI, has garnered enormous investment in accessing accelerated computing via Python. And GPUs as the engine of AI, well, GPUs are just becoming more and more ubiquitous. And so we've seen developers who are interested in AI and learn Python. But then they look around and they dig a bit deeper and they get curious and they get interested and look under the hood about what makes this thing tick. What's underneath their high-level framework? And they look laterally at other domains about how the things that they're learning when they look into how this thing ticks, how that can help in other places. And so there's this influx of cross-domain interest in high-performance computing spurred by all of the things that are happening in AI. And one of the things we've seen at NVIDIA is we've seen this just enormous explosion of interest in CUDA as a result, this wave, as people look deeper to what's going on underneath. And this slide is about one library. It's just representative. This is cuBLAS, linear algebra. But since we put this on PyPy 18 months ago, it's exploded. 3x downloads in 18 months. And we've just, I think, done 1 billion downloads of our Python-hosted libraries just this year. It's unprecedented. The uptake is insane. And one of the reasons to be inspired is we hear about big science producing all of these amazing stories of AI transforming scientific projects. We've had Nobel Prizes recently recognizing these contributions. And I think that's a really inspiring direction of how AI can help science. But one of the brightest honors at the Supercomputing Conference is the Gordon Bell Prize, which fundamentally recognizes exceptional achievements in high-performance computing. And here we're also, as NVIDIA, celebrating these fundamental contributions to accelerated computing on systems that are across diverse fields, including molecular dynamics, protein design, genomics, climate modeling. We've had a bunch in materials science. And one of the reasons is that underlying both is this concept of accelerated computing, this combination of software and hardware working together to make a single problem go faster. And so I think that a lot of people have asked me questions about what do you think about AI, science, AI sort of taking over the design of these systems? Isn't that a bad thing? Or woe is me? And I think actually quite the opposite. I think that it's actually really critical that these systems have some sort of day job, something that drives the economics of investment in them. Just the way that earlier, 20 years ago when I joined NVIDIA, there was gaming and graphics, and that was driving billions of dollars of investment in what was ultimately going to benefit systems for science. Now we have this Gen AI day job that's driving enormous investment. And the real cool thing here is it's driving investment not only in the hardware, but also in the software, in this case in Python, the Python ecosystem. So it's a great opportunity. It's not without some work, because it's not going to look exactly the way that one might expect, but especially because Python is there and some unique attributes of how Python is designed, the fact that it's an imperative language that's runtime compilable. It's got a real easy adoption curve, the way that it allows software to compose. There's a bunch of these attributes that I think are going to make the accessibility to accelerated computing even more widely possible. And we're seeing this happen in the big science domain. We see that users want this software with GPU capabilities. And so there's a couple of themes that I'm going to touch on in the talk today. The software and the systems working together, building for the foundations of GPU computing and accelerated computing, building composability with existing software. So you've got the software and the systems. And then algorithms and Amdahl bottlenecks. Algorithms are the algorithms that allow you to take advantage of these architectures to make some particular problem go fast. And Amdahl bottlenecks, Amdahl is the law that basically says if you speed up something by 10 times, but you've got a little bit left over that wasn't sped up, very quickly that little leftover piece is going to come to dominate the runtime of your application. And Amdahl is something that we've dealt with in accelerated computing a lot, because we get big speed ups on a bunch of the algorithms, and then Amdahl comes and you've got the part that's left over, and that's hard. That is often spread across lots of lines of code, across lots of modules, the way things are integrated, deep assumptions in how frameworks were built. And so the algorithms in the Amdahl, choosing the right algorithms, but then also figuring out ways to overcome the bottlenecks of software integration, or I/O. And then when you scale across multiple nodes, because Moore's law has ended, the only way you can get more performance is by ganging more computational units together. If you want more performance, that means going distributed. And that basically compounds these aspects of software integration and I/O. So the great news is we're starting to see the trend as systems are being designed now. For example, with Doudna, we've specifically got a target for Python in that system. I think this is really important to be thinking about the Pythonic ecosystem for these big science projects. But we're also seeing a lot of progress elsewhere in computational science, especially with tight integration of experimental science with computational science. So explosions in data rates and putting processing near to experiments is basically enabling us to have computational instruments. And increasingly we're seeing Python being actually a key component of that, making it something that makes that computational instrument more readily accessible and quickly adaptable. An example here with the Allen Radio Telescope array and some work we've done with SETI. Typically they're downloading data offline. In this case, this is a detection of a pulsar signal and some radio astronomy data. And moving to online detection, here the thing we worked on was this holoscan framework, which enabled them to do direct data movement from the sensor to the processing on the GPU rather than going through a disk-based flow. Now they can do online processing detection. They can do real-time beamforming to either hone in on a signal or they can, filter something out. This is, widely important to things like multi-messenger astronomy, right, where you want to take detection in one instrument and then point a lot of other instruments across the globe at that to capture other dimensions of the signal or things like that. Now, as I go through these, there's a couple examples. I'm going to note here at the bottom, there's a reference to actually a talk at SciPy that either upcoming or has already happened. You can watch the recording about a bunch of this work. Another example is the National Synchrotron Light Source at Brookhaven National Lab. Synchrotron light source is basically just a high-powered, often X-ray light source that uses a powerful microscope for materials. And here again, currently the sensor data is offloaded offline for processing, and requires a full data set to be captured and done before you can see it and then processed. And it doesn't seem like it's too bad to take 2 minutes to see this stuff, but you think about it. You've put in a request, you've got funding, somebody's handed you this really expensive camera, and there's no viewfinder, and you don't know if the lens cap is actually on, you don't even know if it's on sample, and you might have to shoot a bunch of times to try and actually get it on sample. It's kind of a waste. And so without real-time feedback, you don't have that level of productivity, let alone doing some of the next steps of things. You're just trying to get the instrument to work well. So again here, using that holoscan framework to enable remote memory access and streaming processing, incremental processing, we're able to let the National Synchrotron Light Source do real-time progressive imaging. And so you can actually see very quickly if you're actually capturing what you need to do. So that's like a first step. Okay, great, we can see if the lens cap is on or off. But then in the future, that's going to allow higher data rate captures, which means that you're going to actually be able to get higher resolution and things like that because you're actually able to process and filter online. This is another example here, work on data processing for the Nancy Grace Roman Space Telescope, which is an infrared observatory, looks at the whole sky. It's got obviously high data rate ingestion. And one of the things that I think is really fun about this particular work is this is an example where the work wasn't done by a bunch of computer science PhDs who were supporting it. This is actually work done by the scientists and physicists themselves, the astronomers that are working on this proposal. They're actually able to pick up some of the tools that I'm going to talk about here. In this case, it was CuPy and the NVMath Python framework to get incredibly high levels of performance with just a very little bit of work. And finally, an example from SLAC, where the free electron laser there, they were in a similar state as the synchrotron light source, where they basically had to download and process a lot of data offline. And they wanted to get that to online. So they used a framework called CuPy Numeric, which is a distributed drop-in for NumPy and SciPy algorithms to scale their code across a GPU cluster to get a 6 times speed up their beamline processing. So now they've gone from minutes to seconds. And based upon that, they're now able to make a proposal for the next version of their light source, where their current processing today can only really address about 1% of the proposed data ingest that new light source can produce. But they now see a path to scaling the processing because they've done that work with the current light source. And all of these, I think, are great examples. They're all done in Python. And it's an opportunity for the Python ecosystem to bring new solutions rapidly to all of these different domains by being the catalyst for the solution to these algorithm plus AMDAL problems, these software plus system problems. And that's because accelerated computing is this full stack optimization problem where you've got to attack these problems wherever in the hierarchy, whether it's a high-level problem or a low-level problem, a bottleneck, high or low, you need to be able to attack it anywhere along that stack. And so it needs to be a complete stack. You have to have the ability to go to any layer of abstraction and attack a problem there. And that really informed our thinking about CUDA Python. So I think there's a great opportunity here to provide the tools needed for that accelerated computing. And NVIDIA is providing core SDKs, frameworks, and platforms to make that easier working with you. And one of the ways that we're increasingly working with you is through open source. The frameworks, the innovation we're doing is increasingly in open source, which is key to enabling rapid collaboration, feedback, and integration. And one of the things we're really prioritizing here is the velocity of adoption. It's one of the things we measure. And it's an ecosystem that actually we ourselves use. Here's a list of a bunch of the projects that we engage with, we use ourselves, we contribute back to, and we support through NumFocus Foundation, Python Software Foundation, PyTorch Foundation, because enabling accelerated computing is something we feel there is much work to be done, and this is one of the most effective ways to get that work done. In part because I mentioned these systems are quite complicated. So this is just a picture kind of like laying out all the pieces and parts, the building blocks of a modern large-scale system for accelerated computing. Not just for AI. This is great for AI, but this is also really great for scientific computing. And it includes all of the components. NVIDIA works not just on GPUs, though that's what we're historically famous for. We work on CPUs. We build our own CPUs. We build networking chips and and switch chips. We work on the racks and the cooling and the infrastructure, the power to bring all of this together. And mapping onto a system like this means that you've got to have all of that whole stack that I talked about. Integration from the algorithms, all of the integration across the bottlenecks. We've all got to have that optimized for a system that looks like this. But building the software for this would be really hard if you had to have one of these to build the software. You'd have this chicken and egg cycle. You'd be stuck. So one of the things that we decided to do was to build this little guy. This cute little guy is DGX Spark. Unfortunately, this is just an appearance engineering unit. It's not functional, so I can't run any cool stuff on it for you. But it's exactly the same architecture that was in that big cluster diagram for all of the dimensions that really matter from a software perspective. It's got a GB10 Grace Blackwell chip in it. That's the same architecture as these bigger systems. It's got a 20-core ARM CPU. It's got a powerful Blackwell GPU. It's got 128 gigabytes of CPU-GPU unified memory, the same way that those Grace Blackwell server systems do, which gives the GPU access to not only a lot more memory directly accessible to it, but also that's where all of the I/O lands. And so one of the cool things, I'm going to do this because, like Jensen, I'm going to show you the back of this thing. There's these two ports on the back here that look kind of funky, these little square ports. They are 100 gigabit Ethernet GBIC ports for a high bandwidth Ethernet connector connected to a CX7 SmartNIC. And so this is kind of a unique little box because it's cute and tiny and you can just have it there on your desk next to your laptop. But you can use those high bandwidth ports to connect a couple of these together, which is a pretty cool thing to do, fun experiment. But I think also really interestingly, you can use these to connect to high data rate instruments. So you've got 200 gigabit ports on there that can do direct RDMA into that unified 128 gigabytes of unified memory between the CPU and the GPU. So I am super excited to see what people do with these things. I think it's going to be amazing. I can't tell you when you're going to be able to get your hands on one of them just yet, but they're going to be available from, I think there's a list of all of the different OEMs that we're working with on there. So it's not just from NVIDIA, but there's going to be a lot of people that are making essentially the same thing as this. And we really want to be able to get this into your hands. So you have one of these, because this, I think, is going to be a really great development platform for building up and testing the software stack that scales up even to the big systems. So let's go to the next level deeper. CUDA Python stack. Software, systems, algorithms, OMDAL. We're going to start with a single node in the software stack for that and work down across layers of abstraction from the highest level of abstraction down to the most fine-grained control. And then we'll go and talk about multi-node and distributed programs. So for those that may not know, CUDA has sort of three basic layers to an application. There's the host sort of CPU side, often the existing application, making library calls or CUDA launch calls to what we call CUDA grids, which is the first layer of parallelism. And then those grids are subdivided into blocks, and that's the next layer of parallelism. And then there's a third layer. It's the threads, CUDA threads. You got those sort of three layers of parallelism, and that's going to match sort of the layers of abstraction that I'm going to walk down and talking about the CUDA Python stack. So the first and best way to adopt CUDA is not to invent a new algorithm or write some low-level code, but to stand on the shoulders of giants and use some great stuff that somebody's already written for you. These are typically in libraries, library calls. And NVIDIA, we've actually invested across the last 20 years in building a bunch of these ourselves that fully utilize the NVIDIA platform, all the different GPUs, and make sure that the key algorithms that power science are embodied in these. For example, if you do computational lithography, there's a library for that, cuLitho. Helps manufacture science and manufacturing in the chip making industry. Basically does inverse convolutions really fast for people doing quantum interference for pattern making. You got cuOpt, which is basically a really cool thing. I was never sure we were actually going to be able to put linear programming on a GPU, but the cuOpt team did it. Generalized optimization problems. Everything from like package routing to pipe routing in a factory, or lots of interesting things in scheduling. cuDSS is another example, direct sparse solvers. That's used in a lot of different areas across engineering and computing. And so there's a number of these libraries. We've been building for 20 years. I think we at this point are well over 900 different libraries and associated AI models now that actually work with those libraries. So this is the first place to start. It's where most people actually do most of their work, is calling one of these libraries either from us or from the ecosystem. And as I mentioned at the beginning of the talk, these things, we're increasingly putting them all through native Python interfaces, so they're just there for you. So what about all the other parts of CUDA? Oftentimes I get people who think that CUDA is just CUDA C++, that's what they've heard about the most. But CUDA is actually an entire deep stack of technologies, broad stack of technologies across different languages, across capabilities from developer tools and profilers and compilers and libraries, as I mentioned. NVIDIA has about 200, maybe a little over 200 SDKs of different kinds, not just libraries, but frameworks, compiler interfaces, tuning APIs, profiling APIs. So this is a snapshot, just a tiny snapshot of what's there. So when I think of CUDA, when my team works on CUDA, this is the world that they think about. And one of the keys in this, that's a design principle that's been there from the very start, is interoperability. Interoperability across systems and time, so that what you invest in software doesn't get outdated just because the hardware changed underneath you. And also integration across the different layers, so that when you do work at one layer, you can always drop into a lower layer or move into a higher layer to augment that or solve a problem. This is what I talked about accelerated computing being a full stack problem. And so if you have a problem and there's a bottleneck with something that you're doing at a higher level of abstraction, there is a way to go and solve that by doing something more customized at a lower level that will just work and drop in place. That composability, I think, is really key. and really informed what we decided to do with CUDA Python, which is something that we've been working on for several years. It's taken us a while. But we didn't want to just take bindings of the APIs that we already had developed mostly in C and C++ and just bring that to the Python community and say, call these. We actually wanted to reimagine what the CUDA platform would look like through a primarily Pythonic lens. What would it look like to enable Pythonic use at all of those different levels of the stack? Everything from the developer tools and the libraries, but also to the compilers and the language that you actually write to write low-level tuned kernels. So that a Pythonista should not need to step outside of Python to solve any of those problems. So you have a full toolkit to solve those problems. So one of the core pieces of doing that, at the next layer, you've gone from calling libraries now to the next thing where you're invoking CUDA grids. And that has two parts to it. It has dispatching, so actually telling the GPU to do something, and then there's the what the GPU is going to do. So the first thing we did is we created this thing called CUDA Core, which is open source. It's purely Pythonic object model for CUDA to think about all of the data movement, all of the dispatching needs, all of the setup needs, the bookkeeping needs that allow you to write the host to GPU interface when you get to that next level of building a CUDA program. You've got full in-process execution flow through runtime compilation, so you can do online execution just in the way Python would want to for seamless dispatch. The other part is, okay, now you want to start the what. What are you going to actually run as your algorithms? So one of the things that we did to make that easier, you're still not writing, low-level CUDA yet. You're now at the next level of abstraction of using a bunch of standard algorithms. So we had these for a long time in C++. They were libraries called Thrust and Cub. You may have heard of those. And we brought those in a natively Pythonic way via these things we call the CUDA parallel and the CUDA cooperative libraries. And CUDA parallel, you can think about it as a way to take a standard set of algorithms, sorts, scans, filters, matches, things like that, across common data structures, and it'll run across an entire GPU. So these are sort of coarser-grained operations. And then CUDA cooperative is the next level down, where you've basically got library calls for those same kinds of operations that run inside CUDA blocks and CUDA threads. So you don't have to write a lot of custom code. You have these Pythonic APIs that allow you to call common algorithms at the next level of granularity. Another really powerful tool at this level of granularity is NVMath Python. This slide is the one slide that we all agreed was going to be like cross your eyes in this talk. It's got so much on it. But the main takeaway from this, other than like, wow, that's really complex, is think about walking into a huge library, one of those things with like great columns and huge windows. Why they have windows in a library, I don't know. But huge columns, windows, and just stacks and stacks of scrolls and books going back. And NVIDIA has built probably well over 250,000 different tunable kernels across our libraries. These are the primitives that our libraries are built out of. And imagine walking into a library, a magical library that has all those in it, and in front of you is this desk, and you can ask it, please compose a custom book for me, picking from the right kernels in that library and make it for me. NVMath Python is that tool. It allows you to start with the common linear algebra, signal processing, whatever domain libraries that you're starting to use, but you say, I need a bit more performance. Maybe I need to fuse some operations together because the producer-consumer of that data is so tight that it's going to be more efficient if I take that FFT and I embed it inside this operation that I'm doing. And that expressiveness might not be there in the standard library interfaces, but with NVMath Python, you can take those and construct the thing that you need very straightforwardly. It's integrated with the JIT compiler, so it can do that fusion even online. It's an incredibly powerful tool for that next level of abstraction. And you still haven't even had to learn how to program the actual, low level of CUDA threads yet. And then finally, we get to one of the things that I think I'm super excited about At the next level down, this is where you're now actually starting to write code for the CUDA kernel itself, customizing it. I mentioned there's these 3 layers of execution in CUDA. You've got the grids that are invoked by the CPU. You've got the blocks. Blocks, you're usually got many of those blocks that are oversubscribing a big GPU, and then you've got the threads. The threading model that CUDA has exposed, where you might have 250,000 threads on a processor, has been incredibly powerful, particularly in part because the way that the program is actually compiled down is the same way largely that compilers have operated for the last 60 years. There are some additional tweaks to make it parallel for a GPU, but this attribute of the hardware architecture has made it such that the compiler can actually take advantage of like the last 60 years of compiler optimizations to produce really, really fast code that then can be parallelized across a GPU. So this has actually been an incredibly powerful tool, but it does mean that you have to express, 250,000 way parallelism at the end of the day to write your algorithm. And one of the things that's really unique about Python is that it's really well suited to array-based programming. And so one of the things that we were inspired to do as part of this was to really make array-based programming not at the thread level, but at a higher level of abstraction, the block level, something that's a fundamental primitive in CUDA. This is something we call CUTILE, and it's something that we're bringing first to our CUDA Python platform. And eventually we're actually going to make it available in other CUDA languages as well, but we're starting with CUDA Python. And so let's talk about this block level model. Instead of threads operating on elements, so this very fine grain, you have blocks that operate on tensors or tiles of data. If you've done way back vector-based programming, this is pretty familiar to you. In fact, there have been a number of these languages that have done this on GPU even before CUTILE's come out. OpenAI's Triton in the AI community is a good example of this. And these array-based models are, I think, a much more natural fit for a lot of Python programmers. So it's going to be, I think, a really good match. There's some example code here that talks about how the tiles map onto, for example, elements of your vectors, elements of your matrices, and so it's a really natural fit. The implicit thread parallelism that original CUDA had was really great for very simple array-based programming or certain algorithms that don't map well to vectors, like a sort or a scan or these type of things that often end up producing a lot of data movement if you don't have really fine-grained data control. But for large tensor-based programs, which is a lot of the work that we do, this CUTILE level programming gives you a very simple way to write very tuned custom low-level code. And the great part about it being part of the core CUDA platform is that it gives you all of those compatibilities that I mentioned. It's compatible up and down the stack, integrating with all of the tools, all of the developer tools, the profilers, the debuggers, and it's also got the guarantee of compatibility across different versions of our hardware because we can retarget it to different implementations, especially of the tensor core, which is the really high-powered matrix math unit that's in our recent GPUs. So now I want to shift gears a little bit and talk about the AMDAL part of single GPU programming, which is integrating software together and eliminating overheads. Computing on a GPU, and especially Python programs, they're an integration. They make it really easy to integrate a lot of different software together. But at those interfaces between different software packages, there are often overheads. There are mismatches in format. There are synchronizations that are not fully optimized. And this is where I think some of the most pressing work that we see to do is coming up. And that is to make sure that at one hand, we're not changing the fundamental abstractions that people are using here. On the one side, we have the compute APIs that people might use, whether that's something like Pandas or NetworkX for graph processing or SciPy. We want to retain the structure as much as possible of applications that have already been written and map those on to accelerated primitives through things like common standards for array APIs. At the same time, we we want to make sure that as data is being passed and synchronization is being passed between packages underneath these frameworks, that it's retaining all of the optimizations that are there around data placement, zero copy, and things like that. So investing in these data compatibility APIs, CUPI, the CUDA array format, DLPAC, NumPy's array format, making sure that those things are complete and able to capture the full vocabulary of optimizations, the expressiveness that's needed. And when we do that, we get really great results. An example here where we integrated the cuGraph accelerated graph library underneath the NetworkX API as an abstraction. As a result, we've got a really high performance mapping of NetworkX primitives down onto accelerated computing, and we still have the usability and portability of NetworkX programs. And this is something that we're doing across a number of different frameworks and libraries. And this is an area where if you're interested in giving us advice, giving us feedback, helping on this stuff, definitely come by the table and talk to us. This is a key area where we want to expand this approach. Let's shift gears to multi-node, multi-GPU, and distributed programming. So there's a spectrum of trade-offs here. Parallel computing is always a trade-off between concurrency and degrees of parallelism. You want more parallelism, you're going to be spreading things out across more distributed computing units. And so there's a number of different approaches that are going to be available. Not one size will fit all, but they all need to work with each other. On the one end, we have highly productive frameworks, often that have an implicit single thread of control. That is, they don't have a concept of threads, parallelism. They may not even have a concept of tasking. And Python actually, because of its heritage, has a really good affinity for those kinds of implicit parallel models. And so one example of that I mentioned a bit earlier is CUPI Numeric, which is built on a software stack that I'll talk a little bit more about, that takes advantage of the implicit single thread of control in NumPy programs that gives you an opportunity to now implicitly parallelize them across large-scale systems. But at the other end of the spectrum, you may also need really fine-grained control, all the way down to distributed shared memory. And so one of the things that we actually just made available, I think the last week here has just come out, is our NVShmem API has now got a Python, native Python interface to it. So if you want absolutely fine-grained control over put and get type primitive operations directly from Python, there's a way to do that even within the GPU. So underneath CUPI Numeric, which implements NumPy, SciPy APIs, there is this runtime called Legate, and this is an interesting approach. It's a runtime approach rather than a compiler approach to finding and exploiting data parallelism in the application. And so it's got that same sort of like that compute API, compatibility here with NumPy, SciPy, and the example I'm going to cite here also Boost. And the other side, it's got plugins that allow it to interoperate with data formats from Pandas, from CUPI, for example, and have an abstraction for that data record that can be moved optimally, mapped optimally across the system. Fundamentally, Legate takes in a set of primitive operations as tasks. Some library writer has to build that. That's turned into an event graph based on data dependencies that are discovered and communicated down to a distributed runtime system. That looks a little bit like this. And fundamentally, that's, make this a bit bigger for myself. Fundamentally, that creates a separation of concerns where you've got now an implicit runtime that doesn't know anything about parallelism, that can be remapped across different size systems based on that task graph and the dependencies and the data layout. This is all open source work. It's based off work that started over a decade ago, I think at Stanford. And this is a direction that we're really leaning into to provide one way of high productivity engagement with large scale systems that can be retargeted across different generations and different sizes of systems. And it's starting to pay off. We have some examples where customers, this is in the finance industry actually, want to process really large data sizes that don't fit into smaller systems. In this case, an 8 terabyte problem size that wouldn't fit in memory with XGBoost. They were able to use the Boost version running on Leagate with CUPI numeric and get scalable performance across many nodes. And the code, I think that the interesting part of that, because of the separation of concerns, if you look at the code, it's actually a really small code to write that distributed algorithm. And because the algorithm can be retargeted even to a single GPU, single system, you can run and test the exact same code on a system this big. And so you've got the same code base across multiple systems, testable on multiple systems. So in conclusion, I think we've got a lot of great opportunity ahead of us. We've got great interest in Python and high-performance computing in Python generated by the explosion of the AI industry. We've got some great touch points with NVIDIA to collaborate with us on. This one is really exciting, the Accelerated Computing Hub. It's open source Creative Commons on GitHub. It's where we're depositing all of our samples, our learning material. Come engage there, use it, give us feedback, file GitHub issues on it. We'd love to have you engage with that. We've obviously got a big team here. Come find us at the booth, talk to us more. Here's a quick reference of the different sessions that have been or upcoming here at SciPy where NVIDIA folks are engaged. And with that, thank you very much.
Hi everyone, we have about 10 minutes for questions. Reminder, the Lunch and Learn channel, and I'll maybe go ahead and star the ones you like the most, and I'll read them off for Chris. We'll start with a question from Ed Rogers. It says, thank NVIDIA for supporting this conference. As you say, Python is the language of AI, but in recent years, major corporation backers have pulled back. They've reduced sponsorship, cut Python teams, and slowed hiring. From your perspective, what can the Python community do to help companies see the value in continuing their support?
That's a very good question. I think a lot of it has to do with engagement and conversation with industry. My perspective has been that some of industry thinks long term, but there's a lot in this world that forces companies to think much shorter term than maybe they would like to. And to find long-term alignment, where there's sustainable support, requires really having not just the surface level conversations, but pretty deep conversations, finding the right people within the industry where you can find that connection. And so it's not easy. I think it just requires people and time, and that means it basically needs to be a focus of effort to make those connections.
Thank you. Next question from Julie Hollick. Which fields of science/domains do you think have the most potential for discovery with the use of accelerated computing?
Ooh. Wow. That's like being a kid in a candy store. I don't know. I will not claim to be a scientist myself, so I don't actually have any inside knowledge on the science. But some of the ones that I am most excited about are weather and climate, in particular because the combination of computational methods, pure accelerated computing, and AI surrogate models, I think, has a real tremendous opportunity because AI tends to actually be really good, like uncannily good at modeling chaotic systems. And so coupling surrogate models for AI that are data-driven with computational models that are actually constrained by the physics, I'm very hopeful will give us tools that allow us to simulate various strategies, intervention outcomes, things that we may want to do. And as soon as people get more real-time feedback on their ideas, they're much more likely to actually do something. And so that's one thing that I'm really hopeful about. The other one I'm actually really hopeful about is actually fusion. because plasma instability is actually, again, one of these very chaotic systems in something like a tokamak. And so I'm very convinced that accelerated computing, providing, say, high-fidelity simulations of plasma instabilities used to train surrogate AI models to provide real-time control feedback for fusion stability. I'm pretty super excited about that.
Very nice. Next question should be a softball. Are there any string comparison libraries available in CUDA?
String comparison licenses, yes. Go take a look at CUDA Parallel and CUDA and CUDA Cooperative.
Awesome.
CUDF, I think, also has some good stuff at higher level stuff. I think it's CUDF.
If you need to find more details, meet us at the booth. There are CUDF folks in the room. And then next question for Max Klein, is NVIDIA's CPU x86 or is it a custom architecture? And if custom, why?
Ooh, so yes, we have an ARM core in our CPU. There's an ARM core in this thing, and there's a compatible ARM core in the big server CPU. I think technically it's based on licensed ARM CPU core designs, but ultimately the design of the CPU, one of the things that we realized is, well, stepping back one, accelerated computing at the very beginning, we kind of always said it wasn't just about the GPU, it's really about the best system, which actually includes the best GPU and the best CPU. They've got to work together on the right part because the CPU is kind of like a serial thread accelerator and the GPU is a parallel accelerator. And what we realized, we had the opportunity to build a better CPU single thread accelerator for the GPUs. And a lot of that had to do with not only the single core threaded performance, but actually a lot of the I/O systems around multi-core aspects of the CPU, the memory system, and the way that it interfaces with the GPU via a dedicated interface. And so it's really about that integration that caused us to go and do something new there.
All right, next question is coming up. A long one. All right, Matt. All right, you show examples like the Roman telescope and NVIDIA libraries accelerating flagship science that is happening now. Can you talk about your relationship between NVIDIA and these experiments?
Our relationship between NVIDIA and these experiments. So oftentimes, these experiments are developers who come through our developer program and engage with us, and then we have resources that can engage with them as well. It basically depends on the particular situation, but basically our developer program is the way to do it.
And I'd say follow up with us at the booth and we can get you more information.